right, hello everyone. This is Anna Bergstrom again, and we are back within carbonate equilibria, and we're talking about alkalinity. So, our learning objective for this section, by the end of the video, students will be able to describe how alkalinity is measured, how it buffers hydrogen ion activity in water, and how it sets abundance of other components in the carbonate system. So before we dive into alkalinity, let's quickly review the carbonate system. So recall that we have carbon in gas, aqueous, and solid form. And in previous lectures, we discussed the carbonate reaction series, which involved the dissolution of CO2 into water. So that becomes aqueous CO2. This is going to react with that water and form carbonic acid. And then that carbonic acid is going to dissociate into bicarbonate. Plus one proton. And then that bicarbonate can further dissociate into carbonate and yield another proton. Okay, so this involved carbon gas, and in the previous lecture we talked a lot about how the concentration of CO2 in our atmosphere can affect the shifting along the carbonate equilibrium. But what about the solid form of carbonate? So how does, for example, calcium carbonate, our calcite, come into the picture? Well, if we have calcium ions in water, we can precipitate out calcium carbonate. Or if, conversely, for example, water is running through limestone through some calcium carbonate, we can dissolve that calcium carbonate and we can make calcium ions and carbonate ions. So the relative concentration of our carbonate can similarly have an effect on the entire carbonate system and shift it in one direction or another. So remember that the relative concentration of species is dependent on pH. So we can see here we have this figure where pH is on the x-axis and our molar fraction of our total dissolved inorganic carbon is on the y-axis. And as we move from lower pH to higher pH, we shift from carbonic acid to bicarbonate to carbonate. So because these carbonate and bicarbonate species can accept hydrogen ions, they are affecting the total number of hydrogen ions in solution we have, which is the definition of pH. So if we have higher concentrations of bicarbonate and or carbonate, we can buffer how many hydrogen ions we have in solution and be resistant to a change in pH. So this carbonate system is a really important factor in water chemistry, and it also is important for a huge range of functions. So everything from how your body regulates itself, your blood pH relies on the carbonate equilibrium, and into more conventional things that we're thinking about for this class, like wastewater treatment. The pH and the ability of the carbonate buffer system to maintain an even pH is really important for wastewater treatment. So that ability to buffer pH is called alkalinity. And something that's important to remember here is it's not just the opposite of pH. So the definition of alkalinity, one definition is a measure of acid neutralizing capability or acid buffering. So we can define total alkalinity as the concentration of our bicarbonate species, the concentration plus the concentration of our carbonate species, plus the concentration of our hydrogen ions, minus the concentration of our hydrogen ions. I think I said hydrogen ions twice. So plus the concentration of our OH minus the concentration of our hydrogen ions. And one thing I want to point out here is because carbonate is 2 minus, we need to double the concentration of our carbonate because it can accept 2 protons. So it has twice the acid neutralizing power relative to bicarbonate or OH. Okay, so how do we measure alkalinity? So alkalinity, once again, is our ability to resist a change in pH. So we can think of it, another definition is the sum of all titratable bases down to a pH of 4.5. And why 4.5? Basically because at that pH, all OH has been consumed. Okay, so we can measure this experimentally by determining how much acid it takes to lower the pH to 4.5. So we can see, this is what these students are doing in this picture. They have that burette and they're slowly dripping in acid until that solution that they're measuring the alkalinity of, which is in that volumetric flask that girl is holding, until that solution reaches a pH of 4.5. And then you can use the volume of acid you introduced into that solution to determine what your alkalinity is. And so alkalinity is expressed as a concentration, and we'll get into that in just a second. So in most natural waters, our pH is between about 6.5 and 8.5. And so 6.5 is right here, and 8.5 is right here. So we can see when we're in this window of the majority of our natural waters, by and large, the total, the dominant DIC species is bicarbonate. Okay, so keep that in mind when we move into this next piece. So our total alkalinity is this definition that we use, which is the sum of bicarbonate concentration, carbonate concentration, OH concentration, and then we subtract out our hydrogen ions. However, there's another definition that is carbonate alkalinity. And so carbonate alkalinity truly is a concentration of bicarbonate and carbonate, because both our bicarbonate and our carbonate can accept those protons and buffer. However, when we're working in most natural waters, our dominant species is bicarbonate. So frequently we just calculate our carbonate alkalinity as the concentration of bicarbonate in our solution. So you might see total alkalinity, you might see carbonate alkalinity. There's a bit of a difference in that when we're thinking about carbonate alkalinity, we're only thinking about our DIC species. Okay, so the units of alkalinity, alkalinity is frequently expressed in units of milligrams per liter as calcium carbonate. And the reason why is it's essentially used to indicate how much calcium carbonate we would need to dissolve in that water to produce a solution of equal alkalinity. So that's alkalinity. We know that the overall concentration of our carbonate species is really important because they can accept electrons and they can buffer, they can accept those hydrogen ions and they can buffer our system and maintain a more neutral pH. And bicarbonate in most natural waters is going to be the dominant carbon species, inorganic carbon species, that will be doing that work and buffering and resisting a change in pH. Okay, so before we wrap up, I just want to give a little bonus material, and that is to quickly run through what hardness is, because at least I used to personally get alkalinity and hardness confused, and that's because this idea of calcium carbonate was frequently involved in, or is involved in, both. So hardness is water hardness. It is a property of water quality, and what it is the concentration of multivalent cations, so mostly calcium and magnesium. And those multivalent cations can really influence our water. So in terms of what that looks like when you're in your house, you can end up getting these films of scum on in your shower, for example. Also, hard water makes it really hard for things like your soaps to suds. You end up getting not very sudsy soap if you have really hard water. So what the solution is, what people do, and you may have a water softener in your house is to have a water softener, which you add salt to your water softener and you allow your water to move through that salt, and that's going to dissolve some of those ions and complex with your calcium and magnesium and reduce the hardness of your water. So the main source of calcium and magnesium is limestone and dolomite. And so this graph, we can see our relative concentration in our basins across the United States of hardness. And once again, hardness, just to make it even more confusing, hardness is also expressed in the same units of alkalinity. So that is as milligrams per liter as calcium carbonate. And one thing that's interesting to point out is you'll notice places where we had ancient inland shallow seas that are now functioning as our aquifers are places where we had limestone and now we have hard water. All right, so thanks for tuning in for this lecture, and we will continue on in the carbonate equilibria in subsequent lectures.